Hi, welcome to Digital Electronics, chapter number 2, Numerical Representative. I'm going to talk more very detailed on binary system and arithmetic. So this is the outline of chapter 2, but we're going to focus on the first subchapter 2.1, binary system and arithmetic. So the learning of outcome of this chapter including you're able to describe the importance of positional number system, understand the binary system, able to convert decimal to binary or binary to decimal, this including new representative which is octal and also hexadecimal. Hexadecimal usually have a base on 16, you can see the example over here, and octal will have a base of 8. Describe what is the digital codes and also able to explain the need of error detection in digital system. This is common number system. We have a decimal, which is the normal we are using all the time. This is base to 10. The symbols are from 0 to 9. It can be understood by any human, normal, but however, the computer doesn't work on this system. The computer usually work on the binary system, which is they are base to 2. The symbols are 0 and 1. And also they have an extra system which is octal and hexa. Hexa is back base to 8. The symbols are including from 0 to 7, and hexa, which is base to 16, are the symbol from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We cannot say 10 is going to change to A, B, C, D, E, and last is F. Understanding your decimal numbers. Decimal numbers have two parts. One is this is the decimal point. This is the normal decimal numbers, the whole numbers, which is to the power of a base of 10 and power of tens. These are usually increased in weight with a power of 10. And in the under the fraction decimal numbers, usually is power to -1, -2, -3, and so on. These are some one of the example. Let's say you have 51.5 to the base of 10. Actually, it can be changed to this mode. This is your decimal. Decimal is going over here. This is the number 1. Your number 1 is going to be here. Number 5 is going to be here. And another 5 fractional will be over here. This number 1 is actually to the power of 10 to the power of 0. The 1 times 10 to the power of 0. And this 5 is actually 5 to the power of 5 times 10 to the power of 1, which is 50. And over here, which is 1. When you total out 50 plus 1, that's why you got 51. You can see over here. And also for the fraction, you have a 0.5. 0.5 times to the 10 to the power of -1, you're going to have 0.5. When you add up over here, you're going to have 51.5. That's why you end up 51.5. Under the binary numbers, it is very important to use binary numbers because it's very accurate, easy to implement at any condition because it only have a possible of two numbers, either 0 or 1. For example, you have a ship over here trying to communicate with another ship. So trying to send out a signal from this ship to another ship. So let's say you have a soldier is going to use a light. So when there is a low voltage or maybe you shut down the light, you're going to be 0. And when you on the light, you're going to be 1. So you can send a information like 100110010, and another ship over here can receive this number. So this is basically a binary communication that happened. So let's see on very detail about binary numbers. You have a decimal from 0 to 15. So these are the representative binary numbers. Let's say you have a 0 for decimal. The binary numbers are 0, 0, 0. When you have a decimal 1, you're going to be 0, 0, 1. And when you have a number 2, you're going to be 0, 0, 1, 0. So how you get this one? Is exactly is 1 plus another 1. So 1 plus 1 is going to be 2. Same over here, 1 plus 1 is going to be 0. You're going to have a carry 1. So same goes to the next one. Number 3 is going to plus another 1 plus. So you're going to put the 1 over here, and then the carry just follow as normal, 1 to 1. And number 4, when you have already full over here, you plus another 1, it's going to be 0, carry forward to another 0 over here, and carry forward to another new bit. That will become 1, 0, 0, and so on. For example, number 7, it already have a maximum 3 bits. And for number 8 decimal, you need to add, when you plus another 1, so this is already maximum, so it will become the new bit, number 4 bit will be used, and others going to be 1, 0, 0, 0. And number 15 is the maximum for 4 bit, and for the 16 decimal, you're going to be have 1, 0, 0, 0, 0. More discussion about this, especially on the overflow, will be discussed later. Let's understand the binary numbers, which is power of 2. In a whole number, you have a 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and so on. This is the binary point over here. Under the fraction numbers, you're going to have 2 to the power of -1, 2 to the power of -2, and 2 to the power of -3. So this is an example. Let's say you want to convert a binary number, which is 11.012 to the decimal. So then you have to treat both place at respective. This is our whole numbers, and these are the fraction numbers. The whole numbers, you just put 1 and 1 over here. This is a bit number 2, this is bit number 1. For the bit number 1, 1 times 2 to the power of 0, and you're going to have 1 to times 1, and you're going to have 1 at the end. For this type, follow the same procedure, you're going to have 2 over here. 2 plus 1 going to have a 3 at the end. But it's not finished yet. How about the fraction numbers? Like here, you have 0 and 1. So you have 0 and 1. For 0, this is the representative. 0 times 2 to the power of -1 going to have 0 times 0 times 0.5, which is 0. And this part, 1 to the times of 2 times -2 going to have 0.25. When you total this both, you're going to have 3.25 to the base of 10. So this is a self-task for yourself to understand. So try to complete the table below and convert the binary to decimal as follows. These are answers. So we are going to decimal to change converted to binary conversion. There are 3 methods to be used. The first method is sum of weight method, which is you have to know the whole sum, and then you have to convert to the respective decimal. For example, number 3, 12. You can break it up to 8 plus 4, and then plus 0 and plus 0. This is the imaginary part. So this is later on I will explain more detail on this one. So 12 is equals to 8 plus 4. So 8 is a representative of 2 to the power of 3, and 4 is 2 to the power of 2. So when you have a unit over here, you're going to represent at 1, and when you have a unit here, it's going to represent 1. So is it finished? 12 is equal to 1 to the power of 2 to the base of 2? No. You still have an imaginary of 2 power of 1 and 2 power of 0. Over here, there is no representative. That's why they have having 0, and 0. Don't forget, you can follow, you can see the steps. 2 to the power of 0, 2 to the power of 1, 2 to the power of 2 over here. That's why it happens like this. And finally, 12 decimal will have 1100 to the power of negative to the base of 2 as the answer. Let's see example number 4. 33. It can break it down to 32 plus 1. 32 is the representative 2 to the power of 5, and 1 is the representative of 2 to the power of 0. That's why you have, so the 2 to the power of 0 is 1, represented over here. 2 to the power of 1 is 0. 2 to the power of 2 is 0. 2 to the power of 3 is 0. 2 to the power of 4 is 0. And 2 to the power of 5 is 1. So that's why 33 is equivalent to 100,001 to the base of 2. So second method is to have a repeated division by 2 method. This is how you just divide by 2 and keep the remainder. For example, you have 12 to the base of 10. Have to convert to binary. So 12 you divide by 2. 12 is divided by 2 is 6. And then you don't have any carry. That's why you put a 0 over here. 6 is divided by 2 is 3. That's why you have a 3 over here, and you don't have a remainder is 0 over here. And 3 divided by 2 is 1, and another remainder is 1 over here. And 1 divided by 2 is considered as 0, and you have a remainder 1. So the MSB is at the bottom and LSB at the top. So how you're going to do is you have to from bottom to up. So you're going to have 1 1 0 0 1 1 0 0 to the base of 2. The third method is to repeat the repeated multiply by 2 method. This one is more to the decimal fraction. So let's say you have a 0.3125 to the base of 10, and you have to find the equivalent binary numbers. 0.3125 times 2, you're going to have 0.625. Because there is no remainder, as there is no value in front, so the remainder going to be 0 over here. So just bring the 0.625 to here and times by 2 again. Repeat. You're going to have 1.25. Bring your 1 to here as a remainder and 0.25 over here. 0.25 times 2, you're going to have 0.5, and you're going to have a remainder 0. 0.5 times 2, you're going to have 1, and you just bring your 1 over here. And for this one is from the top to bottom. So this is the MSB and this is the LSB. So you just write 0 dot. This one is from the, because it's already a 0 in front. So you're going to be 0.010101 to the base of 2. So this is the self-task 2. Please, you have 3 questions over here. Convert the decimal to binary using sum of weight. This one is using division by 2 method. And this one is using division by 2 method. To multiple by 2 method. I'm sorry, there is a mistake over here. So this is the answer. And the current learning outcome of this particular subchapter, you're able to describe the importance of position number system, understand the binary system, and able to convert from decimal to binary and binary to back to decimal. So this is the binary arithmetic for additional. Let's say you want to add up 0 plus 0, it should be 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is going to be 0, carry forward 1. For subtraction, 0 minus 0 is going to be 1. 0 minus 1, you have to borrow in front, so you're going to have 1 and borrow 1. 1 minus 0 is going to be 0, and 1 minus 1 is going to be 1 minus 0 is going to be 1. This one is 1. And 1 minus 1 is going to be 0. And multiplication, 0 times 0 is going to be 0. 0 times 1 going to be 0. 1 times 0 going to be 0. 1 times 1 going to be 1. Binary additional multiplication. So how you add two binary numbers. 1 plus 1. If you see over the chart over here, 1 plus 1, it should be 0, carry forward 1. So 1 plus 1 is 0, carry forward to 1. And this one, you add up over here, you're going to have 1 over here. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1, 0, carry forward to 1. That's why you end up 1, 0, 1, 1, 1, 0. For multiplication, 101 times 100. So first, you need to do the first layer, which is 1 times 0 is 0, 0 times 0 is 0, 1 times 0 is 0. 1 times 0 is 0, 0 times 0 is 0, 1 times 0 is 0. And last but not least, 1 times 1 is going to be 1, 0 times 1 is 0, and 1 to 1 is 1. And final result, just add up according to the bits, the row, and it's going to end up 1, 0, 1, 0, 0. This is somehow similar to any basic mathematics. So let's go for the by subtraction. Normal subtraction, you're going to have, let's say we have 4 minus 3. So 4 minus 3 is very simple, just 1 as a result. Let's say we do in the binary subtraction. So 4 is equivalent to 0, 1, 0, 0. And 3 is equivalent to 0, 0, 1, 1. So when you minus 0, 1, 0, 0 to 0, 0, 1, 1. So 0 over here, you have to borrow in front, another times borrow, and you're going to have 1 over here. So 1 minus 1, 1 to the 0, carry 1 minus 1 is going to have 1 over here. Since you already have a borrow over here, so you're going to have 1, 0 minus 1 is 0, and 0 minus 0 is 0, and 0 minus 0 is 0. So when you convert back, 0, 0, 0, 1 is going to have 1 over here. So we managed to subtract and obtain similar to mathematics. But how about a small number minus a big number? Let's say minus 4 plus 3. So this minus 4, you should have a minus over here. 4 is equivalent over here, 0, 1, 0, 0, 0, 1, 0, 0. And you have a 3 over here is going to be 0, 0, 1, 1. So how are you going to do here? So you're going to have a similar results, because you are going to have so you have to borrow from here. You're going to have 1, have 0 minus 1 is 1, and you're going to 1 minus 0 is 1, and suddenly you're going to have a representative of 0 minus over here. Then how are you going to represent a negative symbol if only 0 and 1 is allowed, and the result is not matched to the final of mathematics solution? So this is a question that we are going to be answered in the next topic 2.2. So lay on until then, thank you.